Hey everyone, and welcome to the Artificial Intelligence to Very Intelligence Launchpad Masterclass. Today, we're taking a seriously incredible journey. We're going to trace the entire life cycle of data, starting from how we actually fetch raw information out there in the wild on the web, all the way to how we bring it back to our local workbench to analyze it like absolute pros using Python. If you've ever found yourself wondering how modern apps actually talk to each other or how they make sense of massive data sets, well, you're in the exact right place. Alright, let's dive right into this. Here is our roadmap for getting from the wild web to our clean data workbench. First up, interprocess communication with JSON. Second, routing data with requests. Third, Pandas data mastery. Fourth, slicing and feature engineering. And finally, strategies for missing data. So let's kick things off with Section 1, Interprocess Communication with JSON. Now, whenever a client, say, a web user interface you're clicking around on, needs to talk to a backend server, they've got to agree on a common language, right? And today, that universal language is JSON. It is an incredibly efficient, universally understood, industry standard, and it's structured entirely as simple name-value pairs. Honestly, if you look at it, it looks almost exactly like a standard Python dictionary. You might see a bracket, then quote, name, Alice, comma, age, 30. It's beautifully simple. But there's a bit of a catch. Because JSON comes across the web as a flat string, Python can't natively perform math or run conditional checks on it. We actually have to translate it first. To fix that, we use Python's built-in JSON library, which basically acts as our universal translator between network-friendly and Python-friendly formats. It pulls this off using 4 main functions. If you receive a string from the web, you just use json.loads to load it right into a Python dictionary. If you're reading from a saved file, it's just json.load. And when you're ready to send your own data back out, you just do the exact reverse. json.dumps converts your dictionary back into a transport-ready string. And json.dump writes it straight to a file. Simple as that. Moving right along to Section 2, routing data with requests. Okay, so we know the language, but how are we actually sending the message? Enter our transport delivery vehicle, the requests library. This is what lets us call REST APIs and handle the HTTP protocol. Now, when you ask a server for something, you generally use one of 2 methods, GET or POST. We use GET requests when we just want to ask a server to provide data. It's super straightforward. But everything you ask for is exposed right there in the open URL. POST requests, on the other hand, are what we use to safely send hidden data payloads. Think user IDs, passwords, that sort of thing. POST is vastly superior for security and for handling large payload sizes, mostly because the requests library automatically converts your Python dictionary into a hidden JSON payload entirely behind the scenes. So understanding how we structure the information we do expose in a GET request is totally crucial. We do this through parameters, and they basically come in 2 flavors. Path parameters are added directly to the URL structure with slashes like /1. They act as a direct map to a specific resource. Query parameters are tacked on to the very end of a URL right after a question mark. Think of things like Q equals Mumbai or format equals JSON. These are your filters and modifiers. They tell the server exactly how you want your data sorted or formatted. Once you fire off that request, the server's going to talk back using an HTTP status code. A 200 series means success. You got what you asked for. A 400 series means there was a client error, like the classic 404, meaning you typed an unreachable URL. And a 500 series means the server itself actually had an internal error and crashed. Now, why does this matter to us? Well, in the real world, the internet drops, servers fail, and usually right when you're on a tight deadline. So, you absolutely must always wrap your API calls in try except blocks, catching that connection error, and always include a timeout parameter. This ensures you're building robust code that won't just freeze forever if a server goes down. Oh, and a quick side note. If you're practicing this at home, the old CoinDesk crypto API we used to use is actually retired now. So I'd recommend swapping your URL to CoinGecko for your GET requests. Alright, section 3. Pandas Data Mastery. Now, let's completely shift gears. We're parking our transport vehicle, we've pulled the data, and now it's time to sit down at the data analyst's workbench with Python's absolute powerhouse library, Pandas. Pandas basically stores data in two main ways. You've got a series, which is just a one-dimensional list, but the real star of the show is the data frame. To quote our source material here, the data frame is the absolute game changer. This two-dimensional structure looks and behaves exactly like an Excel spreadsheet or a SQL table. You can literally load massive datasets into a data frame with a single line of code like pd.readsysv. It's kind of magic. Let's see how this builds out, because this is where your exploratory data analysis or EDA workflow really starts. The second you load that data, you want to run these exact steps. First, head and tail to preview the top and bottom rows. Second, shape to grab your exact row and column count. Third, info to check out your data types and spot any immediate missing values. And fourth, describe, which instantly spits out this heavy-hitting statistical summary for every numerical column. Means, minimums, maximums, the whole shebang. You can also throw in value counts and unique to quickly tally up distinct categories. Moving to section 4, slicing and feature engineering. Of course, as an analyst, you almost never want to look at the entire massive data set all at once. Your job is to isolate specific data. Say you're hunting for laptops over $500. You can filter for this by writing logical conditions inside brackets, using AND or OR operators, literally exactly like you'd build an if statement in core Python. But when it comes to extracting specific rows, you have two primary tools. And you absolutely need to know the difference between them. iloc and LOC. iloc stands for index location. It operates purely on numerical integer indices, just like a standard Python list. If you ask for rows 0 to 5, it stops at the exclusive bound of n-1, giving you 0, 1, 2, 3, and 4. But LOC or location uses textual row names, and crucially, it is inclusive of the upper bound. If you give LOC a range of 0 to 5, it returns rows 0 through 5 inclusive. So definitely pay very close attention to your bounds when you're slicing. And this brilliantly illustrates what happens when we want to create brand new data from our existing slices, which is called feature engineering. Take a look at the sales and cost columns here. If you want to figure out profit, you don't have to write some complex messy for loop to iterate through a million rows, no way. You just write a simple mathematical operation, subtracting cost from sales, and Pandas instantly calculates the difference for every single row, generating a brand new column to store the results. It is breathtakingly fast. Finally, section 5, strategies for missing data. But what happens when that fancy math breaks down because your data is flawed? The real world is incredibly messy, and datasets are pretty much never perfect. Which brings us to the final step of our data pipeline, handling incomplete records. Whenever you have an empty or corrupt field, Pandas represents it as NaN, not a number. Before you can fix these blank spots, you actually have to find them. You do this using the isNull method, which scans your whole data frame and highlights exactly where your data pipeline is bleeding. Once you've tracked down those NN values, you've got 4 escalating tiers of sophistication to deal with them. The easiest is just dropping the data, using dropna, which removes the entire incomplete row. That's great if you have massive amounts of data and can afford the loss. Just try not to induce panic by accidentally dropping your whole dataset. Next up is fill data using fillna, where you replace blanks with a designated standard, like the mathematical average of that column. Then we can get a bit fancier with interpolate. which examines the known data points before and after a gap to figure out the overarching trend and fill the cell intelligently. And finally, for time series data, there's backfill or bfill, which just copies the next known valid data point backward to bridge the gap. Pro tip for your own workflows: always make sure you've actually uploaded your CSV files to your coding environment first before running these scripts. And definitely, don't be afraid to keep cheat sheets from PyPI or Geeks for Geeks handy. So, let's recap. We have successfully pulled our data from the web using JSON and requests. We loaded it onto our Pandas workbench, we sliced it, we engineered new features, and we cleaned out all those messy NaN values. We now have a mathematically perfect spreadsheet. But that leaves us with one massive lingering question. We've mastered fetching and manipulating raw data into clean spreadsheets. But how do we actually bring these numbers to life? How do we make people care about them? Keep that thought in your head, because next time we'll be tackling NumPy for complex arrays and diving into the beautiful visual storytelling of Matplotlib and Seaborn. See you then.